Okay, so we're going to talk about parametric equations. Parametric is a word you might have heard before, but you haven't really learned about it in math. You do know about vectors, and I'm going to show you why we learn about parametric right after we learn about vectors, because they are related. So let's just start with something that you can easily visualize. It says, consider a raindrop that falls from a cloud under the force of gravity, and at the same time it is blown horizontally by the wind. So this is definitely something that you should see, and this is what would happen. No raindrop would probably ever fall straight to the ground. It would be blown horizontally. In this case, we're going to assume the simplest case scenario, which is just a straight horizontal wind, which is, we're not even considering direction. Okay, so even this, we're going to have to kind of simplify. But it says, since both its horizontal position, which is going to be x, and the height y vary with time, x and y can both be written as functions of time using parametric equations. So look what we have here. We have two linear equations, okay? One for the horizontal position, one for the height, and they both vary with time linearly. Now, between the two of them, we're not quite sure if that relationship will be linear or not. We need to kind of look at this in more detail. And pretty much almost everything we do in this lesson is going to be maybe not the most simplest case, but a simple case since we're just starting out here. Okay, so I'm going to draw a picture here, and here's going to be the height, which is obviously going to be, from gravity here. It's going to cause that raindrop to go down. And then also we've got the horizontal wind. And if you're thinking, hey, gravity isn't linear, it's quadratic, don't let that throw you off too much. It has to do with the relationship between variables, and we're thinking simplest case scenario here, so don't let this throw you off too much. All right, because we're going to get to that, the whole deal with gravity. It's going to be the whole lesson tomorrow. All right, so if I have these two vectors and I place them head to tail, I then have a resultant vector, okay? And this is going to be the actual path of this raindrop. And so that's why we're studying this with vectors. We're going to bring in, the cosine horizontal and sine vertical aspect of vectors into tomorrow's lesson. For today, we're just going to kind of get used to this notation of parametric equations, okay? So if you want to think of it this way, t is like a third variable. Normally we only have two variables, x and y, and usually x is independent and y is dependent. Well, here, x and y are both dependent upon t, and t is the only independent variable. In this case, t represents time, and so it makes sense that t is independent and that anything else then would be dependent upon it. So let's talk about how you would evaluate these. It's pretty much going to be what you think, but let's set up a t-chart. This is how you did variables in the very beginning. Now keep in mind that both x and y are both dependent upon t. So I'm going to set up some numbers for t. I could set up many numbers, but I'm going to set up these. Just basic 0, 1, 2, 3. And then I'm going to use the equation to find my x variable. So when t is 0, x is going to be 0. When t is 1, 1 times 3 is 3. Then we've got 2 times 3 is 6, 9. And if you look at this column, just the x's, notice that there's a constant, adding change. You add 3 each time. That means that x is linear. And we already knew x was linear based off of the equation, but I'm just kind of reinforcing it. Okay, now let's think about y. Y is a little bit more complicated, a little bit of number crunching, never hurt anybody. And so when t is 0, y is 23. Now I'm not looking at the middle column, I'm looking at the t column, because I don't know yet how x and y are related to each other. And so 23 minus 5 times 0 is 23. 23 minus 5 times 1, well, that's 18. 23 minus 5 times 2, that's going to be 13. And the last one is 8. And if you notice on these, I'm subtracting 5 on each of these, and that it's also linear, which we already knew, just reinforcing that. Okay, now let's, we did what they told us to do, but I want to take this just a little bit further, kind of show you where you can go with this. Graphing a parametric is something that's difficult to do by hand because of the third variable aspect. It needs to be in real time, and there is a way for your calculator to do that. I'm not going to get too much into it today, but here we have x and here we have y, and we can graph in the regular coordinate plane. Okay, so at this point I am just going to graph these two columns, and these are both my dependent variables in my parametric equation. T is the only independent variable in my parametric equation, but when we graph it on the coordinate plane, it's going to look like x is independent and y is dependent upon x. Okay, so let's think about our first point would be 0, 23. Okay, right here. And then we have 3, 18. So I'm just going to label the coordinates that we need. Let's go ahead and put 3, 6, 9. Then I would have 6, 13, and 9, 8. All right, and what you would want to do is you would want to connect these. And I could actually put an arrow all along this curve to show the path, but this is the resultant vector, so to speak. Okay, and this is the result here is linear. Now this again is simplest case scenario. Now if you had to write the equation of this line in terms of just x and y, how would you do that? Okay, so hopefully you're thinking the slope is down 5 over 3, so that would be negative 5 thirds x, and the y-intercept is 23. You can never forget those good Algebra 1 skills. All right, another way that we could have done this, and this is kind of getting ahead of myself at this example, but we're going to get into it later, is if you think about it this way, if you were to solve for t here, okay, I'm going to do this over here, what would t be in terms of x? It would be 1/3 x. And then if I were to plug it in, you know, almost like solving a system here, I would have 23 minus 5, and instead of t, I wrote 1/3 x. This is why I solved for t. Look at what you'd have here. Y equals 23 minus 5/3 t, which is the exact same equation I came up with. Okay, so we've done a lot with this particular example. All right, there is a parametric mode on your calculator. Not going to show it to you in this lesson because you don't need it for this lesson, but that is something we'll talk about in class. Whoops. Okay, next example. Okay, so notice here I have an x squared, so this is going to be slightly different because although the first one's linear, the second one's quadratic, and so that's, you know, you can kind of guess how that's going to change my graph. I know that's not going to be as simple as linear, 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 okay, but when you're actually plugging in these numbers right here, you don't need a calculator for this, but feel free to use one for all the number crunching. And so they already have the table kind of set up for what the t values that they want you to use. And so if we think about t being -2, if I plug in -2 here, I get -3. If I plug in -1, that's going to give me -1. If I plug in 0, I get 1. And the nice thing about linear equations is that they just are being, you know, the pattern is add the same number each time. So you can kind of use that to your advantage here. And that will work as long as your t's are also going by 1, which they are. Okay, and this is linear. We can tell just by the fact that I'm adding the same number each time, and that number is my slope. Okay, now to do the second equation, this is going to be the quadratic, so the pattern is not going to be as simple as just add the same thing each time. There is a pattern. The pattern is the second difference is the same, but you're better off just to keep plugging in the number. So Negative 2 squared is 4, and 4 minus 3 is 1. Negative 1 squared is 1, minus 3 is negative 2. And the next one is negative 3. The nice thing about quadratics is I do get some symmetry. So 1 and negative 1 should yield the same result. So should 2 and negative 2. Those should yield the same y value. Okay, and this is just kind of reviewing those good algebra skills that you hopefully remember everything from algebra 1 and 2. Alright, so go ahead and make a guess as to what you think if I just graph these two variables, what my result will look like. And then we'll see if you're right or wrong. Now keep in mind that in our parametric equations, both x and y were dependent upon t. T was the independent variable. X and y are both dependent variables. But when we then graph this on a Cartesian or coordinate or xy plane, it's going to be just like how it was before. It's going to appear that the x is the independent and y is actually dependent upon x, but we always have to think back to the situation. But in terms of graphing, you were going to plot these points. Now, I kind of showed it on the last one with that resultant vector, but on this one, you need to keep in mind that you are going in an order. So the order that I'm plotting these points in matters, okay? And so 1, negative 3, 3, negative 2, 5, 1, and 7, 6. I plotted these points in this particular order as the t values were increasing. Okay, this is the order that my parabola, and the result here is a parabola. Now, I'm putting these arrows where I'm putting them. It doesn't matter so much that you put them exactly in between the points. I'm just saying I put them along the way so that you could see that this is the path of this particle. In this case, it's not necessarily a it's not a raindrop anymore. It could be any type of particle. All right, or this is kind of theoretical here, but this is the path. This is the third variable. This is the t. So you may be thinking, well, this is overkill just to have a third variable. But again, we're just talking about parametric equations for the first time. So we've got to get the basis down. We've got to understand the language and the notation. And then, later on in calculus, you get to kind of work up to what the application is. Okay? Now, the result here was quadratic, so you can kind of make for yourself, your own guesses as to if one is linear and one is anything else, would that result follow the higher order polynomial? And so that's not anything you really have to know right now, but it's kind of good to notice that as you go through your assignment in class tomorrow. So on the linear one, it was easy to then look at this graph, okay, and then write an equation. For quadratic, this is not so easy. For someone who was in Algebra 2 and right in the middle of a quadratics unit, they should be able to write the equation of this quadratic. Anybody who hasn't really talked about parabolas very much lately, like all of you watching this video, you're probably going to struggle with writing the equation of this quadratic. I'm not going to review how to do that right now. That's not that important for this particular lesson. But tell me, if you had a set of data and you knew it was quadratic, how could you write the equation if you had to? You could always use quadratic regression, okay? And you only want to use that if you know the data is quadratic, but I can see that it is here, mostly because of the symmetry, but also because the vertical component here, the y component here, was definitely quadratic. Okay, so you could have used quadratic regression here to write this equation. Or there is a way to do it without, but again, not the point of the lesson, so I'm going to move on. Okay, so now we're going to kind of go the other way. In this case, I'm giving you a line with just x and y, and it's linear, obviously. It says line, it's linear. And I'm asking you to write the parametric equations. Now, once again, I'm going to write this down. Remember that t is your true independent variable. Okay, and both x and y are dependent upon t. That's extremely important to remember. So when you write your equations, we could actually be writing our equations as x of t and y of t. You don't have to. It's kind of like f of x or just f. I'm going to keep it simple today. Tomorrow when we actually apply this, you'll see that it will actually be x of t and y of t. So if you have to write two equations down, make the top one as simple as you could possibly make it. And the simplest equation is kind of like the parent function, y equals x, but this is going to be like x equals t. So the horizontal component here is the time component if you want to bring it back to our raindrop problem. Now if x is equal to t and y is equal to 1/2 x plus t, how could you write an equation in terms of y and t? Just replace the x with the t. That's why I made it so simple. Now there are other equations we could have written. This is definitely the simplest one. And if you were to have made a table and graphed these parametric equations, the resulting line, the resultant vector, would definitely be y equals 1/2 x plus 7. So going this way is a lot easier, actually. Okay, now looking at the next example, I'm giving you the parametric again. Notice that they're both linear. I'm asking you to write a line. So it's kind of like what we did on the first example. This is why I said I was almost getting ahead of myself first example. Now, in the first example, let me remind you of how we did it. Okay. I made a table, I made a graph, and then I used my good Algebra 1 skills to come up with an equation of a line just using x and y. And that will work every time. Okay, but you really don't have to do that on every single one of these problems. All right, let's think about the easier way to do this rather than a table and a graph, because it doesn't say we had to do those, so let's not do that. Okay, first what we're going to do is we're going to solve for t. Now I could actually do this in either equation, but I'm going to do it in my first equation. So if I have x equals -2 plus t, what does t equal? Okay, t equals x plus 2. Okay, and so that's first. All right, I'm going to put little bullets here. Okay, then we're going to substitute. And guess which equation we're going to use now? All right, so then I'm going to have y equals 4 minus 3, and instead of t, I'm going to write what t equals, which we just found, x plus 2. Now notice I already have an equation with just an x and a y, and all I need to do is clean it up. So then that's going to be y equals 4 minus 3x minus 6, and then writing this in good slope-intercept form, y equals -3x minus 2. Okay, now let's go ahead and go backwards just for the fun of it. We're almost done. If I gave this to you and asked you to find the parametric, do you think you would have come up with these two? No, probably not. Probably what you would do is say, hey, I'm going to take the easy way out. I'm going to let x equals t, and I'm going to let y equals -3x, -3t minus 2. Okay, now if you look at these two parametric equations, they may seem completely different, and they are basically off by just an subtracting of 2, okay, or this addition of -2. All right, but they would actually yield the same result, which is this graph right here. Okay, that's it. Bring your questions to class.